Welcome, dear listener, to this quiet space where curiosity and calm intertwine. As you settle into your chosen sanctuary, perhaps wrapped in the soft embrace of a blanket, or soothed by the faint rhythm of rain against your window, I invite you to turn your attention towards a question both subtle and profound. What if light could be gently persuaded to slow its speed? We are about to embark on a journey not of distance, but of depth. A journey into one of physics' most elegant questions. Can we slow down the speed of light? This is not a query born of defiance toward nature's laws, but an exploration of how light and matter engage. We will not only witness light not as a mere phenomenon, but as a story, a narrative of constancy and connection, of energy and stillness, of cosmic certainty and human curiosity. But first, take a breath and tell me, where are you joining in from tonight? Are you curled indoors, wrapped in the soft glow of a lamp, or outdoors, beneath a sky sprinkled with stars? Whatever your setting, whatever the hour, I'm glad you are here. So breathe in deeply and allow your awareness to soften like twilight. This is a reminder that you are part of a universe where light connects everything, from the farthest quasar to the quiet pulse of thought within you. You are a witness to wonders both vast and intimate. So let your thoughts settle like starlight on still water. Release the weight of the day and allow your mind to grow quiet, open, and receptive. This is an opportunity to listen to the harmony of physical law. We'll move slowly, like light easing through a dense medium. We'll explore how light interacts with matter, how it can be gently delayed, and how these moments of slowing reveal deeper truths about the nature of reality. If you're ready, let's begin. Let's turn our attention, softly and without effort, to the quiet miracle of light's journey and the possibility of inviting it to rest. Imagine, if you will, a single photon of light. Not a blazing sunbeam, not the harsh glare of a screen, but one gentle messenger. It was born in the furious, silent nuclear heart of a star, untold millions of years ago, a tiny packet of energy bursting into existence. It begins its journey then, a journey across the incomprehensible emptiness of interstellar space. It does not tire, for it has no mass to weary. It does not slow, for it is propelled by the most fundamental rhythm of the universe itself. It moves at a speed so constant, so unwavering, that it is woven into the very fabric of reality, a golden thread in the tapestry of physics. It is the universe's ultimate speedster, the unwavering constant, the absolute cosmic speed limit. And then, after its long, lonely voyage across the light years, navigating the gravitational curves of galaxies and the dark streams of nebulae, it finally arrives here, in our tiny corner of the cosmos. It enters our atmosphere, a delicate veil of gases, and it continues on its way, a minuscule arrow shot from a distant star. It journeys through the cooling evening air, past drifting motes of dust, through the leaves of a sleeping tree until it meets the window of a quiet room where you are settling in for the night. It passes through the glass with a whisper, and in a final, fleeting instant, it meets your eye. A neuron fires. A cascade of signals is sent through the intricate pathways of your brain, and you perceive it. You see a tiny, distant twinkle in the vast, dark blanket of the night sky. That light, which has been traveling for millennia at 299,792,000 458 meters per second, has finally come to a stop, not in space, but in time, transformed from a physical phenomenon into a perception, a memory, a feeling of quiet wonder. It is a beautiful, almost poetic story, one that speaks to the profound constancy and order of the universe, but it also gently nudges the curious mind. Is that speed, that incredible C, as physicists call it, always so absolute? Is it an unbreakable rule etched into the cosmos with indelible ink? Or could it, under the right circumstances, be persuaded, coaxed to change its pace? Could we, one day, not just observe light's incredible, relentless speed, but gently temper it, like a river guided by soft earthen banks, slowing its rush to a meandering flow? This question, which we will explore together in the quiet of this evening, is not one of breaking the laws of physics, but of coming to understand their beautiful, often subtle and deeply layered nuances. It is a question that invites us on a calming journey, not through the vast, cold distances of space, but into the deep, intricate, and surprisingly intimate nature of light itself. To understand how we might even contemplate slowing light, we must first understand what light truly is in its essence. We must push aside the complicated mathematics and the dense textbooks for a moment and think of it not merely as a particle or a wave, but as a story, a narrative written in the language of energy. It is a story of intertwined electric and magnetic fields, each one giving rise to the other in a perfect, self-sustaining cycle, a perpetual motion of the most elegant kind. An electric field shifting and changing instinctively generates a magnetic field at a right angle to it. And that newborn magnetic field, as it fluctuates in turn, gives birth to another electric field. They perpetuate each other, a dance of creation and motion that propels itself forward through the void. This self-propelling dance, this continuous handoff of energy from one field to the other, is what light is. And the tempo of this dance, the rhythm at which these fields oscillate, collapse, and regenerate, is what we perceive as its speed. In the pure, perfect emptiness of a vacuum, where there is nothing to interrupt this intimate dance, no other partners to bump into, no friction to resist, the tempo is at its absolute fastest, its most primal and fundamental state. This is the cosmic speed limit, the C that we know. But space, even the deep, cold space between galaxies, is not a perfect vacuum. It is sprinkled with the faintest wisps of atoms, lonely hydrogen nuclei, and mysterious dark matter. And our atmosphere here on Earth, the thin blue line that protects us, is positively bustling with activity. Molecules of nitrogen and oxygen, water vapor, and dust, all vibrating with their own energy. So what happens when our photon, our elegant dancer, encounters another partner on the dance floor? What happens when light, this ethereal traveler, meets matter? This encounter, this gentle meeting, is not a collision of cosmic proportions, but a subtle, complex interaction, a whispered conversation. And it is here, in this soft dialogue between light and the material it touches, that our story of slowing light truly finds its beginning. It begins not with a dramatic event, not with a roar, but with a gentle, almost imperceptible interaction, a first delicate step in a long and fascinating waltz. To envision this delicate interaction between light and matter, let us leave the vastness of space for a moment and come closer to home. Picture a pane of glass in your window, smooth and seemingly transparent. To our photon, This is not a simple barrier, but an entire universe of atoms, a bustling city of matter. As the light approaches the city, its journey changes. The photon, a ripple of electric and magnetic fields, does not simply crash into the atoms. Instead, its arriving electric field exerts a gentle, almost imperceptible force on the electrons that are bound to those atoms. Think of it as a soft wind passing through a field of tall grass. Each blade of grass, each electron, is subtly stirred, compelled to sway in rhythm with the passing breeze. The electron, charged with energy, begins to oscillate, to vibrate in sympathy with the frequency of the light's own electric field. But an accelerating, oscillating charged particle does something remarkable, something predicted by the gentle hum of Maxwell's equations. It itself becomes a source of light. It generates its own tiny, new electromagnetic wave, its own faint photon, radiating outwards. This is the heart of the interaction. The original light wave, the one from the star, and these newly created waves from the atoms it is passing through, all begin to overlap. They interfere with one another. It is as if the original musical note of the star's light is joined by a chorus of identical notes, all sung by the atoms in the glass. But these new notes are not sung in perfect unison. There is a delay. The atoms take a tiny, almost negligible amount of time to respond to the initial push, to begin their oscillation. This minuscule delay means the waves they produce are slightly out of step or out of phase with the original wave that prompted them. When waves combine like this, they don't just add together simply, they create a new composite wave. The effect of this interference, this blending of the delayed waves with the original, is that the entire precession of the light wave is slowed. Its forward progress is retarded. The peak of the combined wave passes through a given point slightly later than the peak of the original wave would have if it were traveling alone in a vacuum. The dance continues, its fundamental steps unchanged, but it is now moving through a crowded ballroom, and its overall progression across the floor is gentler, more measured. This is why light slows down in materials like water or glass or air. It is not because the photons are crashing and bumping like tiny marbles, losing speed to friction. They are not being absorbed and re-emitted in a stop-start motion, a common misconception. That process would scatter the light in all directions, making the glass opaque and milky. Instead, the light is continuously being regenerated by the atoms it encounters, but this regeneration process, this chorus of atomic voices, introduces a collective delay. The light's phase velocity, the speed at which the crests of its wave move forward, is reduced. And this is not a rare or exotic phenomenon. It is happening all around you, right now. The light from your lamp, should you have one on, has been slowed by the air in your room. The sunlight that poured through your window today was traveling slower through the glass than it was through the vacuum of space. We measured the slowing factor as a material's refractive index. The higher the refractive index, the more the light is slowed. In diamond, for instance, light travels at less than half its vacuum speed, which is why diamonds sparkle so brilliantly. This slowing effect is intimately tied to how the light bends and reflects within the stone. So, in a very real sense, we already slow down light every day. We have done so for centuries, simply by making windows and prisms and eyeglasses. We are already masters of persuading light to amble a little more slowly through certain materials. But this is a passive bulk effect. The light is slowed as it travels through a medium, but the moment it exits back into a vacuum, or the air, it snaps instantly back to its universal constant, c. It is like a traveler walking quickly across open land, slowing to a stroll when moving through a dense forest, then resuming their original pace immediately upon exiting the other side. The question then evolves, becomes more nuanced and far more fascinating. This is not about slowing light within a material, but about slowing light itself. Could we create a state where the light, the photon, is so profoundly, so intimately entangled with matter that its very identity seems to change pace? Could we not just guide it through a forest, but convince the traveler to change their inherent walking speed? To explore this, we must journey from the familiar world of glass and water into a more exotic realm of physics, a world of ultra-cold temperatures and precise atomic control, a world where the boundaries between light and matter begin to softly blur. This journey into a more profound slowing of light invites us to consider not just the material, but the state of the material itself. In our pane of window glass, the atoms are in constant thermal motion, jostling and vibrating with the energy of heat. Their response to the incoming light is chaotic, unorchestrated. Each atom sings its delayed note, but the chorus is slightly out of tune, a hushed cacophony that results in a statistical average, a steady but modest slowing of the light's passage. To truly coax light into a slower gait, we must bring order to this chaos. We must create an environment where the atoms are not jittery individuals, but a collective, a unified medium that can respond to light with a single coherent voice. This requires stillness, not the relative stillness of a quiet room, but an absolute, profound stillness that approaches the ultimate cold, a temperature so low that it is but a whisper above the absolute zero of the universe, where all atomic motion nearly ceases. It is in these frigid, serene realms that the most beautiful experiments in light slowing have been conducted. Scientists use lasers and magnetic fields to trap a cloud of a specific gas, often a metal like rubidium or sodium, and then begin the patient, meticulous process of cooling it. They remove energy, atom by atom, until the cloud is suspended in a vacuum chamber at a temperature only a few millionths of a degree above absolute zero. This state is known as a Bose-Einstein condensate, a phase of matter where atoms lose their individual identities and merge into a single coherent quantum entity, behaving less like discrete particles and more like a single giant wave. It is a superfluid, devoid of all viscosity, a perfect, tranquil quantum lake. And it is into this exquisite, ordered stillness that we now shine our light. But not just any light. A carefully prepared probe, a gentle beam with a very specific color tuned precisely to resonate with the innate energy levels of these ultra-cold atoms. This resonance is the key that unlocks a far deeper interaction than the simple electron oscillations in glass. Here, the light does not just nudge electrons, it engages the very energy states of the entire atom. As the light beam enters this condensate, a miraculous transformation begins. The photons, the particles of light, and the atoms of the condensate become inextricably linked, entangled in a quantum dance. The energy of the photon is absorbed by the collective cloud, but not in the way a rock absorbs sunlight growing warm. This is a coherent absorption. The energy is spread out, shared among the entire condensate, creating a collective excitation, a wave of energy that moves through the atomic cloud. This wave is a curious thing, a hybrid entity that is part light, part matter. Physicists call it a politaron. It is as if the photon has shed its purely ethereal form and put on a cloak of matter, becoming something new, something that carries the properties of both. And because this new entity is part matter, it is heavy. It has inertia. It responds to the world not with the effortless, weightless speed of light, but with the slower, more deliberate pace of an object with mass. The light, in its new politaron form, is now walking through a forest so dense, so still, that its pace is reduced to a crawl. In landmark experiments, scientists have used this exact principle to slow light to speeds of just a few meters per second, slower than a bicycle, slower than a walking person. They have brought light to a pace where we can almost watch it move, a beam of daylight racing at a snail's pace through a cloud of atoms. In these moments, the light is not just being delayed by a medium, its group velocity, the speed at which its information and energy travel, has been dramatically reduced. It is a stunning achievement, a testament to our ability to manipulate the most fundamental aspects of nature. But even here, the photon's fundamental nature is not truly broken. The moment this hybrid polariton reaches the end of the atomic cloud, the matter cloak falls away. The energy is re-radiated, and the photon continues on its journey, instantly resuming its universal constant speed, c, as if its slow stroll through the condensate was but a dream. It has been delayed, yes, profoundly so, but not permanently transformed. The traveler put on heavy boots for a short walk, but then took them off and returned to their fleet-footed ways. This leads us to an even more profound and restful question, a question that sits at the very edge of theoretical physics and peaceful contemplation. If we can slow light to a walking pace, could we ever bring it to a complete and utter standstill? Could we capture a photon, a thing that by its very nature must move at the speed of light, and hold it, store it, like a butterfly suspended in amber, preserving its information and energy not in moving atoms, but in perfect, motionless stillness? The answer, wonderfully, is yes. And the method is not one of force, but of gentle persuasion, a symphony of quantum mechanics so elegant it feels less like physics and more like poetry. The notion of bringing light to a complete and utter standstill feels like a paradox, a gentle contradiction in terms. It seems to ask a river to become a photograph of itself, to request that a song become a silent score on a page, denying the very essence of what it is. Light is motion, is energy in transit, is the universe's constant messenger. To ask it to stop is to ask it to cease being itself. Yet, within the serene and profoundly ordered world of the ultra-cold atom cloud, within the hushed confines of a laboratory that feels more like a temple to quantum mechanics, physicists have achieved precisely this marvel. They have learned not to force light to stop, for force would only destroy it, scattering its energy into useless heat. Instead, they have mastered the art of gentle persuasion, of convincing light to pause, to willingly transfer its story, its intricate quantum information, into the patient, waiting memory of matter, to be held in trust until it is called for again. This process is a delicate and intricate ballet, far more nuanced than simply slowing the light's march. It is a symphony of control, a testament to our ability to speak the subtle language of the atomic world. It begins, as before, with the creation of a cloud of atoms, often rubidium, cooled to a near standstill, a Bose-Einstein condensate. This is not merely a gas. It is a single quantum object, a superatom, its millions of constituents humming with a unified frequency, a choir ready to sing in perfect harmony. Into this prepared and tranquil medium, a carefully tuned probe beam of light is sent, a soft pulse containing a specific quantum signature, a particular polarization, a phase, a precise amount of energy. Its photons engage with the atoms, and through the process of resonance, they form the hybrid polaritons, those fascinating part light, part matter creatures that amble so slowly through the forest of atoms. But then comes the masterstroke, the series of moves that transforms the slow walk into a perfect, motionless pause. The scientists, with exquisite control, gradually alter the conditions within the cloud. They might change a magnetic field with infinite patience, or ever so slightly shift the frequency of a second, controlling laser beam that is bathing the entire cloud in a specific light. This control laser is the conductor of this atomic orchestra. Its subtle change is like gently adjusting the tuning of a vast cosmic radio, bringing it into a more and more precise station. What this adjustment does is alter the resonant frequency of the entire atomic ensemble in a very specific way. The cloud's inherent ability to absorb and hold the light's energy is dramatically, almost miraculously increased. This leads to a state physicists call electromagnetically induced transparency, a name that sounds complex but describes a beautiful and almost paradoxical phenomenon. By shining this precise control laser onto the atoms, they are actually made transparent to a specific frequency of the probe light. It's as if the dense forest is commanded to become perfectly clear for a specific type of traveler. But this transparency comes with a profound side effect. It creates a tremendously steep, almost cliff-like gradient in the cloud's refractive index. It is the steepness that is the key to the final, ultimate slowing. The light, in its polariton form, feels this changing landscape. Its pace, already slow, reduces further and further still, becoming a glacial creep. The wave of energy, the pulse of information, compresses upon itself, its leading edge slowing more than its trailing edge, bunching up like a slinky being pushed together. The physicists continued their gentle adjustment of the control laser, deepening the transparency condition, steepening the refractive index gradient further. The light's group velocity, the speed of its information, drops through mere meters per second to centimeters per second until it asymptotically approaches zero. The pulse ceases to move forward. It is spatially compressed, trapped within a tiny region of the cloud, its energy spread out and shared coherently among the atoms. It is hovering. And then, at this precise moment of perfect pause, the control laser is gently, completely turned off. The connection, the precise tuning that allowed this strange miracle, is severed. But the light's information, its quantum state, the specific, unique arrangement of its energy, its phase, its polarization, all the information that made that particular pulse of photons unique, is not lost. It is not absorbed as heat would be, dissipated into the random motion of atoms. Instead, it is mapped with near-perfect fidelity to a specific collective pattern of atomic spins within the cloud. The atoms themselves are now subtly, but definitively different. Their internal energy states have been collectively altered to form a perfect stationary hologram, an atomic imprint of the original light pulse. The light has been transformed. It is no longer light at all. The photons are gone, but their story, their essence, has been transcribed into a different language, the language of atomic spin states. It is as if the beautiful, complex musical note of the light has been translated into the intricate, silent grooves of a vinyl record, holding the potential for the music within its form, silent until placed upon the turntable of the right conditions. The light is stored. It is at rest. For the first time since it was emitted from its source, that particular packet of energy and information is not moving at the speed of light. It is utterly motionless, held in the quantum memory of the atomic cloud. It can be held this way in its atomic form for milliseconds, and with increasing refinement for seconds, and even for minutes, an eternity in the quantum world where coherence is fragile and fleeting. During this time, the light's information is preserved, protected from the decoherence and noise that usually destroys quantum states. It is a form of memory, the most fundamental light storage possible, a silent atomic library holding a story of light. Having gently guided a pulse of light into a state of perfect stillness, having translated its vibrant, fleeting energy into a silent atomic inscription, we're left with a profound and quiet question. What becomes of this captured story? Is it destined to remain forever frozen, a fossil of light locked in a crystal of ultra-cold matter? Or can the process be reversed? Can we beckon the light back from its slumber, asking the atoms to release the story they hold, to let the music play once more? This act of retrieval is not a simple reversal, not a mere rewinding of a tape. It is a reawakening, a delicate rekindling of a fire from its embers, and it requires the same exquisite care and control as the storage itself. The atomic cloud, now no longer a transparent medium, but a living library, holds the information not as a physical object might hold a stain, but as a group of people might hold a complex melody in their memory, ready to hum it back in unison when given the cue. This cue is the return of the conductor, the control laser. After the predetermined storage time, a span of heartbeats in the quantum realm, the scientists begin the process of revival. With the same infinite patience they employed to slow the light, they now gradually restore the conditions that define the cloud's state of electromagnetically induced transparency. The control laser is gently turned back on, its frequency and intensity carefully dialed to the precise same values they held at the moment the light was captured. This is not a sudden flash, it is a slow dawning. As the control laser illuminates the cloud once more, it realigns the atomic spins, it retunes the vast atomic radio back to the exact station it was set to before the light was captured. This realignment is the signal for the atoms to begin their collective performance. The precise pattern of energy states that was imprinted upon them, the atomic hologram of the light pulse, now has a pathway to express itself. The energy, held coherently across the entire system, begins to reorganize. The atomic spins, processing in their memorized pattern, start to generate a new electromagnetic field. It is the inverse of the absorption process. Just as an accelerating charge generates light, the coordinated collective motion of these atomic dipoles begins to radiate. A new photon, or rather, a new pulse of photons, is born from the cloud. But this is no random emission. Because the information was stored coherently across the entire system, the re-emission is also coherent. The atoms act not as individuals, but as a single entity, singing the light back into existence in a unified voice. The released light pulse is not a faded copy or a distorted echo. It is a faithful reconstruction, carrying the same quantum identity, the same phase, polarization, and energy structure as the original pulse of light that entered the cloud what felt like a lifetime ago. It emerges from the far side of the atomic cloud, and in that moment of emergence, the polariton cloak falls away completely. The light, once again a pure photon or set of photons, snaps back to its universal constant speed, c, racing away into the vacuum of the chamber as if its long pause had never happened. To an observer, it would appear as if a pulse of light was sent into a cloud, disappeared for a measurable amount of time, and then miraculously reappeared on the other side, completely unchanged, as if it had simply been waiting in a hidden dimension. This successful storage and retrieval is one of the most elegant demonstrations in all of physics. It proves that information, the most ephemeral of things, can be decoupled from its physical medium, held in a state of potential, and then made manifest again without loss. It is the quantum equivalent of a breath being held and then released, unchanged. The implications of this stretch far beyond the serene cold of the laboratory, touching upon the very future of how we might communicate and compute. This ability to stop light, to hold it, and to release it on demand forms the cornerstone of a technology that is still in its infancy, but holds immense promise, the quantum repeater. In our current world, We send information flying through glass fibers as pulses of light. But over immense distances, even light weakens and scatters. To amplify the signal, we must use repeaters that read the light, convert it into electrical signals, amplify those, and then convert them back into light. This works for classical information, but it destroys the delicate quantum state of a photon, its specific phase and polarization, which is essential for technologies like quantum cryptography, which promises perfectly secure communication, and quantum computing, which leverages these fragile states to perform calculations impossible for classical machines. A quantum repeater based on stopped light would function differently. Instead of reading the photon, it would allow the photon to hand off its quantum information directly to a cloud of atoms at a relay station. The information would be stored safely in the atomic memory, immune to the noise of the outside world. Then, once the next link in the chain is ready, the atoms would be instructed to re-emit the photon, perfectly intact, to travel the next segment of its journey. In this way, the quantum state could be faithfully teleported across global distances, never being measured, never being destroyed. It is a concept that bridges the tangible and the ethereal, using the pausing of light to enable a new kind of connection. The successful capture and subsequent re-emission of a light pulse, a process that feels less like engineering and more like a form of gentle quantum poetry, opens a door to possibilities that stretch far beyond the hushed, ultra-cold confines of the laboratory. It invites us to consider a future where the flow of information itself is not a relentless, unstoppable current, but a medium that can be pondered, stored, and thoughtfully curated. This ability to stop light, to persuade it to pause its eternal journey, and deposit its story into the patient memory of matter, forms the cornerstone of a technology that is still in its delicate infancy, but holds a promise so profound it could reshape the landscape of global communication and computation. To understand this, we must first gently examine the limitations of our current digital world. Our modern existence is built upon a frenetic exchange of information encoded in pulses of light that race through vast networks of glass fibers, crisscrossing the ocean floors and spanning the continents. These photons carry our conversations, our data, our connections. But light, for all its speed, is not impervious to the world it travels through. Over these immense distances, even the purest glass fiber introduces a faint whisper of resistance, absorption and scattering. The light pulse weakens, its signal fading like a distant star being swallowed by the dawn. To combat this, we employ signal repeaters. These are not passive devices, they are active interpreters. They must detect the arriving weakened light pulse, convert it into an analog whisper into a digital electrical signal, amplify that signal, and then use a laser to generate a completely new, fresh pulse of light to continue the journey. This process works magnificently for classical information, for the ones and zeros that constitute an email or a video stream, but it operates with a heavy hand. In the act of measurement and recreation, the repeater destroys the original photon. It reads the message, but in doing so, it loses the unique physical essence of the messenger. This presents an insurmountable barrier for the future of quantum information. Quantum technologies, such as quantum cryptography and quantum computing, do not rely on simple ones and zeros. They leverage the delicate, nuanced quantum states of individual photons, their specific phase, their polarization, their entanglement with other distant photons. These states are incredibly fragile. The mere act of observing them, of measuring them to amplify them, irrevocably collapses this quantum information into a classical bit. It's like trying to copy a soap bubble by touching it. The very attempt destroys its beautiful, fragile structure. The promise of perfectly secure communication, where any eavesdropping attempt would disturb the quantum state and be instantly detected, would vanish. The potential of quantum computers to solve problems intractable to classical machines by leveraging superposition and entanglement would be confined to a single, isolated location. This is where the beautiful phenomenon of stopped light offers a different path, a gentler handshake between the quantum and the classical worlds. Imagine, instead of a classical repeater that bullies the photon into being read, a quantum repeater station. This station would not be a noisy electronic hub, but a serene, chilled chamber holding a cloud of atoms prepared as a quantum memory, much like the one we have already described. A photon carrying a fragile quantum state would arrive from the previous segment of its journey. Instead of being measured, it would be invited into this atomic cloud. Through the precise application of a control laser, the photon's quantum information would be seamlessly and coherently transferred into the collective spin states of the atoms. The light would be stopped. Its journey would pause. The quantum information would now reside, safe and sound, in the atomic memory, protected from the decohering noise of the outside world. It could be held there, in its pristine quantum state, for the necessary time. Milliseconds, seconds, waiting. This waiting is crucial. It allows for a process called entanglement purification and quantum error correction to be performed locally at the repeater station, ensuring the information remains perfect. Then, and only then, once the next segment of the optical fiber is confirmed to be ready and the quantum link established, the control laser would be reactivated. The atoms, on cue, would coherently re-radiate the photon. A new photon, yes, but one that is the perfect quantum twin of the original, carrying the exact same phase, polarization, and entanglement links. This newborn photon then continues its journey to the next repeater station, eventually reaching its final destination thousands of kilometers away, with its quantum state perfectly intact. This concept of a quantum repeater, built upon the technology of stopped light and quantum memory, is the key to building a future quantum internet. It would be an internet not of speed, but of fidelity, not of simple data, but of unbreakable security and immense computational power distributed across the globe. It would allow for the teleportation of quantum states between distant quantum computers, effectively linking them into a single, vastly more powerful entity. It is a vision that transforms the act of slowing light from a laboratory curiosity into a foundational technology for a new era of communication, an era built not on the brute force of amplification, but on the subtle, patient, and profound art of preservation and gentle release. As we contemplate the serene, almost meditative process of bringing light to a halt and then coaxing it back into motion, our minds naturally drift from the tangible applications, the quantum repeaters and future internets, toward the deeper, more philosophical currents this ability stirs. The manipulation of light's velocity is not merely a technical triumph. It is an act that gently nudges the most fundamental pillars of our understanding of reality, namely, the nature of causality and the flow of time itself. In our everyday experience, cause and effect are the unbreakable rhythm of the universe. A stone is thrown, and then it splashes in the water. A switch is flipped, and then the light fills the room. The then is sacred, enforced by the speed of light, which is the ultimate messenger of information. Nothing, no signal, no influence, can travel faster than this cosmic speed limit. This ensures that the order of events, the sequence of cause preceding effect, remains inviolate for all observers. It is the principle that maintains a logical, coherent universe. But when we talk of slowing light to a walking pace, or even stopping it entirely, we are playing with the very fabric of this causal order in a localized, controlled environment. Consider a pulse of light that has been slowed to the speed of a bicycle with an especially prepared medium. Within that medium, the light's energy and information are propagating far more slowly than they would in the vacuum outside. This creates a fascinating scenario. If you were to observe two events within this medium, say the firing of a laser and its subsequent detection, the delay between cause and effect would be dramatically elongated. The effect waits for the cause in a way that feels almost palpable. Now, extend this thought experiment further to the theoretical limits. What if we could not only slow a light pulse, but manipulate the medium's properties to create a gradient where light is slowed to different degrees in different sections? In certain hypothetical scenarios, the mathematics of wave propagation within such dispersive media suggests that under very specific and extreme conditions, the group velocity of a pulse, the speed at which its peak travels, could, in theory, become faster than the speed of light in a vacuum, or even become negative, suggesting the pulse's peak exits the medium before it even enters. This is not a violation of Einstein's relativity, but rather a complex trick of wave interference. The information carried by the pulse, the actual cause, cannot travel faster than c. The seemingly superluminal pulse is a reshaped artifact, a new peak emerging from the leading edge of the original pulse due to the intense filtering and reshaping by the medium. It is an illusion of timing, not a true breaking of causality. Yet, even as an illusion, it forces us to refine our understanding of what constitutes a signal. Physics tells us that the true speed of information is not necessarily the speed of the pulse's peak, but the speed of its front, the very first, infinitesimally rise of the wave. And this front velocity, as dictated by the most profound theorems, can never exceed c. These experiments serve as a beautiful, gentle reminder that our common sense notions of speed become deeply nuanced in the quantum realm. They show us that the constant c is not just the speed of photons in a vacuum, it is the speed of causality itself, the ultimate rate at which the universe can process information and establish a relationship between events. By slowing light down, we are, in a very real sense, stretching the local fabric of space-time within that medium, creating a tiny pocket where the universe's clock ticks at a different rhythm for that specific phenomenon. We are creating a bubble of delayed consequence, a domain where effect is persuaded to wait just a little longer for its cause. This does not break the universe's rules, but instead reveals their incredible subtlety and depth. It shows that the law is absolute, causality is protected, but the pathways it can take are far more strange and wondrous than we might have once imagined. It invites a sense of profound peace, not anxiety, for it illustrates that the universe's order is both unbreakable and infinitely creative, allowing for pockets of exquisite slowness within the relentless, constant rush of cosmic time. While our journey has taken us into the serene, controlled realms of laboratories where light is coaxed to a whisper of its normal speed, we must not forget that this phenomenon is not solely a human invention. The universe itself, in its grand and patient artistry, has been slowing light since the first stars began to shine, painting the cosmos with the subtle effects of this gentle delay. We need not look to complex Bose-Einstein condensates to witness this. We can simply step outside and behold the sky. Every sunset is a silent testament to the slowing of light. As the sun dips below the horizon, its light must travel through a much thicker portion of the Earth's atmosphere to reach your eyes than when it is directly overhead. The atmosphere, though seemingly transparent, is a medium, a soup of nitrogen, oxygen, argon, and water molecules. As sunlight passes through this gaseous ocean, its constituent colors, each a different wavelength of light, interact with these molecules in a process called Rayleigh scattering. But beyond the scattering that gives the sky its blue hue, there's the deeper, more pervasive effect of the atmosphere's refractive index. The light is slowed, ever so slightly, as it passes through the denser air near the Earth's surface. This slowing is not uniform. The shorter wavelengths, the blues and violets, are slowed slightly more than the longer red and orange wavelengths. This difference, this dispersion, causes the light to bend, or refract, as it enters the atmosphere at an angle. The setting sun is actually already below the geometric horizon when we see its final glow. The atmosphere acts as a lens, bending the sunlight around the curve of the Earth and presenting us with a mirage of the sun that lingers for those precious extra minutes. The vibrant oranges and deep reds that color the sunset are also a result of this journey. The blue light has been scattered away in all directions by the long atmospheric path, leaving the resilient, less easily scattered reds and oranges to travel straight through to your eyes. A final, slowed down message from the day. A rainbow is another celestial artwork, born from light's slowed and splintered journey. When sunlight encounters a curtain of rain, it does not simply bounce off the back of a water droplet. It enters the droplet, and in that moment, it crosses a boundary into a new medium, water, where its speed is reduced to about 3/4 of its vacuum velocity. This sudden slowing causes the light to bend, or to refract, towards the droplet's center. It then reflects off the inner back surface of the droplet, and as it exits back into the air, it refracts again, slowing once more as it re-enters the denser medium at the edge of the droplet before finally speeding up as it returns to the air. This double refraction and internal reflection is what separates the white sunlight into its glorious spectrum of colors. Each color, from violet to red, slows to a slightly different degree within the water. Each has its own tiny, specific refractive index. Violet light slows the most and bends most sharply, while red light slows slightly less and bends on a gentler curve. This difference in slowing, this dispersion, is what fans the light out into the familiar arc. Without this natural slowing of light within the water droplet, there would be no separation, no band of colors, only a faint white glow. Even the twinkling of stars, or scintillation, is a dance of light being slowed and sped up. The Earth's atmosphere is not a perfectly uniform medium. It is a turbulent fluid, with pockets of warmer and cooler air, each with slightly different densities and therefore slightly different refractive indices. As starlight travels through this shifting, rippling ocean of air, its path is constantly perturbed. It is momentarily slowed and bent by a denser, cooler pocket, then sped up and bent another way by a warmer, less dense one. To our eyes, this rapid, random bending and slight change in the light's apparent speed manifests as a gentle twinkling, a soft, rhythmic flickering that makes the night sky feel alive. The star itself is steady. It is the atmosphere's ever-changing effect on the light's journey that creates the dance. In every case, from the grand canvas of the sunset to the fleeting beauty of a rainbow and the gentle twinkle of a star, we are witnessing the same fundamental principle we explore in the lab: light in dialogue with matter. It is a conversation that changes light's pace, that bends its path, and in doing so, creates some of the most peaceful and awe-inspiring spectacles in the natural world. These phenomena remind us that the physics of light is not an abstract set of equations confined to textbooks, but a living, breathing poetry written across the sky, a daily performance of slowing and bending that invites us to pause, to look up, and to appreciate the subtle, beautiful mechanics of our world. Beyond the transient beauty of atmospheric effects and the profound cold of atomic clouds, there exists another frontier in our quest to gently persuade light to alter its pace, a frontier built not upon temperature, but upon structure. This is the realm of engineered materials, where human ingenuity crafts substances with properties not found in nature, designing them atom by atom, layer by layer, to interact with light in entirely novel ways. Here, we move from observing light's natural dialogues with matter to architecting entirely new conversations, building environments where light can be guided, manipulated, and slowed with an unprecedented degree of control. The most beautiful examples of this are photonic crystals and metamaterials. Imagine a crystal, but not one made of atoms arranged in a repeating pattern to interact with electrons. Instead, envision a material with a periodic variation in its refractive index, a nanoscale tapestry of different substances, each bending light to a slightly different degree, woven together in a precise repeating lattice. This is a photonic crystal. Much as the atomic lattice of a semiconductor creates a band gap that forbids electrons from having certain energies, the nanoscale lattice of a photonic crystal creates a photonic band gap, a range of light frequencies that are forbidden from propagating through the material. At the edges of these band gaps, something remarkable happens. The dispersion relation of the material, the equation describing how the frequency of light relates to its wavelength within the medium, becomes extremely steep. And as we have learned, a very steep dispersion relation results in a very slow group velocity for light. Within the carefully designed architecture of a photonic crystal, light can be made to crawl. It is not being absorbed or stored as in the atomic memory. Instead, its propagation is hindered by the constant interference and scattering within the lattice. The light wave is forced to navigate a labyrinth, its path becoming a convoluted journey that drastically reduces its forward progress. This is not a failure of the light, but a triumph of design. The material itself is engineered to be a maze where light is persuaded to meander. Researchers have crafted photonic crystal waveguides, channels within these crystals that allow light to travel along a defined path, but at speeds orders of magnitude slower than in a vacuum. The light is not a prisoner, it is a guest led on a deliberately elongated tour through an intricate palace of its own design. Then, there are metamaterials, whose name means beyond materials. These are composites, often made of tiny, repeating metallic structures much smaller than the wavelength of light they are designed to influence. While a photonic crystal manipulates light through a periodic structure that creates band gaps, a metamaterial achieves its effects through the resonant properties of these tiny unit cells, each one acting like a miniature antenna, interacting with the electric and magnetic components of light in ways natural atoms cannot. Through this careful engineering, metamaterials can be designed to have a refractive index that is not just high, but negative, a concept that bends the mind as much as it bends light. In such a material, light behaves in counterintuitive ways, and its phase velocity can move in a direction opposite to its flow of energy. While the exotic goal of negative refraction often captures the imagination for applications like invisibility cloaking, in the context of slowing light, metamaterials offer another path. By designing the unit cells to have very strong resonances at specific frequencies, engineers can create regions of extremely high refractive index, which correspondingly dramatically slow the light passing through them. The light is made to linger within these resonant structures, its energy coupling strongly with the engineered atoms of the metamaterial, much like a tuning fork causing another to vibrate sympathetically. This is a more direct, material-based analog to the atomic processes we explored earlier, but achieved through human-made structures rather than ultra-cold atoms. The beauty of these engineered materials lies in their robustness and potential for integration. Unlike a fragile Bose-Einstein condensate that requires immense cooling apparatus, a photonic crystal or metamaterial can operate at room temperature, etched onto a semiconductor chip. This opens the door to practical applications in miniaturized photonic circuits, where slow light could be used to create optical buffers and delay lines, essential components for managing the flow of information in all optical computers and communication networks. Light could be temporarily held in a tiny corridor on a chip, its delay precisely calibrated, allowing data packets to be synchronized without ever needing to be converted into sluggish electrons. These materials represent a different philosophy in our relationship with light. We are no longer just placing obstacles in its path or asking atoms to remember its story. We are constructing entirely new worlds for light to inhabit. Worlds with rules we have written designed to gently and persistently persuade it to slow its eternal rush, and to do so in a way that might one day fit inside the palm of your hand. As we marvel at the intricate methods devised to slow light, from the quantum whispers of ultra-cold atoms to the nanoscale architectures of photonic crystals, a quiet, profound question naturally arises. Is there a fundamental limit to how slow light can be made to go? Or could we, in theory, bring it to such a state of near-perfect rest that its wavefront becomes almost motionless, a frozen ripple in the fabric of space-time? The answer, as with so many things in the gentle embrace of physics, is a tapestry woven from both theoretical boundaries and practical possibilities, each thread revealing a deeper layer of understanding about light, matter, and the universe itself. Theoretically, within the framework of how we currently understand light's interaction with matter, the group velocity of a light pulse can approach zero. We have already seen this in the experiments where light is halted entirely, its information transferred to atomic spin states. In that state, the light, as light, ceases to exist for a time. Its velocity is not just slow, it is undefined, for it is no longer propagating. It is in a state of potential, a paused story. For light that is still propagating, still identifiable as a wave moving through a medium, the group velocity can become astonishingly low, millimeters per second, or even micrometers per second. In such regimes, the pulse of light is so drastically slowed that it would take minutes to cross a single centimeter. It is, for all practical purposes, at a standstill from a human perspective. Yet, even here, there are constraints. The slower the light is made to travel, the more extreme the conditions required. In atomic systems, this demands ever colder temperatures, ever more precise control over external magnetic and optical fields, and an environment increasingly isolated from the faintest whispers of thermal noise and vibration that would disrupt the delicate quantum coherence. In photonic crystals and metamaterials, pushing light to ever slower speeds requires fabricating structures with near-perfect periodicity on atomic scales, a monumental engineering challenge. The materials must be almost flawless, as any defect or irregularity would scatter the light, causing loss, and destroying the very slow light state we wish to create. There is another, more fundamental limit that emerges not from our engineering capabilities, but from the very nature of the slowing process itself. It is a trade-off, a gentle balancing act imposed by the laws of physics. As we slow a light pulse dramatically, we must also compress it spatially. The pulse's energy is squeezed into a smaller and smaller volume within the medium. This compression amplifies the interaction between light and matter, but it also increases the losses due to absorption and scattering. There is a point where, to make the light slower, you must make the medium longer, or the pulse narrower, and eventually the pulse becomes so compressed that it can no longer be distinguished from the noise of the system, or it is simply absorbed as heat. This is the practical limit, the point where the signal vanishes into the background hum of the universe. Furthermore, there is a bandwidth constraint. A medium that slows light tremendously typically does so only for a very narrow range of frequencies, a specific color of light. To slow a pulse carrying complex information, which is composed of a spectrum of frequencies, you would need a medium that can slow all those frequencies equally. Otherwise, the pulse will become distorted, its shape changing as different colors are slowed to different degrees. Creating a material with a high slowing factor and a wide bandwidth is one of the great challenges in the field. So, while the theoretical possibility of light moving at a glacial pace exists, the practical reality is that we are always dancing with these trade-offs between speed and loss, between slowness and bandwidth, between control and complexity. Yet within these boundaries, the possibilities that slow light unveils are nothing short of transformative. Beyond the quantum internet repeaters we already imagined, consider the potential for sensing. A slow light sensor would be exquisitely sensitive. Because the light interacts with the medium for a much longer time, even the faintest trace of a foreign molecule or the subtlest change in pressure or temperature could be detected with unprecedented precision. Imagine environmental monitors that could sense a single pollutant particle in a vast volume of air, or medical sensors that could detect a single biomarker for a disease in a drop of blood, all because light was persuaded to linger and interact with the sample for just a little longer. Or consider the world of computing. Optical buffers that use slow light could temporarily store information entirely as light, eliminating the need to constantly convert between optical and electronic signals, which is a major bottleneck in modern data centers. This could lead to faster, more efficient all-optical processors. And on the most speculative frontier, the ability to control the speed of light with such precision might one day play a role in technologies like analog computers that use light to model complex systems in real time, or even in fundamental experiments that probe the intersection of quantum mechanics and gravity, where the precise control of energy and timing is everything. The dream is not necessarily to stop light everywhere, but to master its flow, to be able to speed it up or slow it down at will, creating a new kind of optics where time, not just space, is a dimension we can design with. In our quiet exploration of light's mutable speed, from the theoretical boundaries to the future possibilities, we have navigated the realms of quantum mechanics and nanoscale engineering. Yet, as we approach the conclusion of this journey, it feels necessary to gently steer our focus back from the microscope and the vacuum chamber to reconnect these profound scientific wonders with the human experience they ultimately serve. For the story of slowing light is not merely a technical narrative, it is a deeply poetic one, a metaphor that resonates with the most fundamental rhythms of our own existence and our perception of the world. Light is our primary narrator of reality. It brings us the story of the distant stars, the colors of a flower, the smile on a loved one's face. Its constant, unwavering speed has shaped our understanding of causality, of distance, and of time itself. To learn that this constancy is not absolute, that this most faithful messenger can be persuaded to linger, is to subtly alter our relationship with the universe. It reveals a cosmos that is not rigid and clockwork, but fluid and filled with nuance. A universe that allows for pockets of slowness, for pauses and reflections within its relentless forward march. This resonates powerfully with our own inner lives. We often perceive time not as a constant tick, but as a variable flow. An hour spent in anxious waiting can feel like an eternity, while an hour lost in a good book or in deep conversation can feel like a fleeting moment. Our consciousness itself seems to have the ability to stretch and compress the subjective experience of time, much like the mediums we have discussed stretch and compress the journey of a light pulse. The scientific pursuit of slowing light mirrors a deep human yearning to sometimes slow down our own lives, to create a buffer against the rush of existence, to find a way to hold on to a beautiful moment just a little longer before it continues on its way, forever beyond our grasp. The atomic memory that holds the story of a photon is, in a way, like our own memory. It takes a fleeting, ephemeral experience, a pulse of light, a moment of joy, and encodes it into a more stable form. a neural pattern, and atomic spin state, where it can be stored, protected from the decay of the immediate present, and recalled later, re-experienced, if not in its original form, then in a faithful reconstruction that carries its essential meaning. Both processes are acts of preservation against the flow of time. And just as the retrieved light pulse is a new entity, yet perfectly faithful to the original, our memories are not perfect recordings, but they carry the truth of the moment forward into the future. There is a gentle comfort in this parallel. It suggests that the laws of physics, in their own elegant way, accommodate the same principles of preservation and recall that are so central to our human experience. Furthermore, the very methods used to slow light speak to a philosophy of gentle interaction rather than forceful control. We do not slow light by crashing into it with a barrier. We slow it by creating an environment of resonance, of understanding, of invitation. We cool atoms to a profound peace so they can sing in harmony with the light. We craft materials with intricate beauty to guide the light on a longer, more meandering path. This is a lesson in patience and subtlety. It is about working with the inherent nature of a thing, persuading it rather than commanding it. In a world that often values speed and force, this is a quiet testament to the power of slowness, of precision, of creating the right conditions for wonder to unfold at its own pace. Finally, this entire field of study is a beautiful reminder that the universe is still full of mystery and softness. The fact that we can take something as fundamental as the speed of light and, within the boundaries of its laws, find such flexibility and creativity is a source of not just intellectual satisfaction, but of profound peace. It tells us that the cosmos is not a rigid, impersonal machine, but a place of infinite subtlety and artistry, where even the most constant rules have depth and texture waiting to be understood. It invites us to approach the world with curiosity and gentleness, to look for the nuances, to appreciate the delays and the pauses, for within them often lies the deepest beauty. As you drift towards sleep, remember that the light from the stars above has traveled for millennia at its immutable pace, but that here, on Earth, we have learned to whisper to it, to ask it to rest a while. And in doing so, we have touched a mystery that connects the quantum to the cosmic and the scientific to the deeply, beautifully human. As we let the concepts of slowed light and paused photons settle in the mind, like dust motes drifting in a sunbeam, it feels right to broaden our gaze once more, to consider not just the light itself, but the very stage upon which this drama unfolds, space and time. For the act of slowing light is not merely a manipulation of a beam, it is a gentle bending of the local rules of the universe, a tiny, controlled echo of the most dramatic warping of all, the kind enacted by gravity itself. This brings us to a point of beautiful convergence, where our delicate laboratory experiments meet the cosmic scale prophecies of Einstein's general theory of relativity. In Einstein's conception, gravity is not a force pulling at a distance, but the curvature of space-time itself by mass and energy. A massive object, like a star or a planet, creates a dip in this four-dimensional fabric, and this curvature dictates the paths that objects, and light, will follow. One of the most profound predictions of this theory is that gravity slows time. A clock ticks more slowly in a stronger gravitational field than it does in a weaker one. This is not a mechanical effect, it is a fundamental property of the universe. Time itself flows at a different rate. And since the speed of light is a constant that connects space and time, this gravitational time dilation has a direct and mesmerizing effect on light. As light climbs out of a gravitational well, away from a planet or a star, it must expend energy. But because light's speed in a vacuum is constant, it cannot slow down. Instead, this energy loss manifests as a change in frequency. the light is redshifted, its wavelength stretches, and its frequency decreases. This is the gravitational redshift. Now consider this from the perspective of a distant observer watching light struggle to escape a tremendously massive object like a black hole. As the light moves through regions of increasingly curved spacetime, the time dilation becomes extreme. To the distant observer, the light appears to be moving infinitely slowly as it approaches the event horizon, the point of no return. Its frequency redshifts towards zero, and it appears to fade away, never quite reaching the horizon from the outsider's perspective. The light is, in effect, being stopped by gravity. It is a natural, cosmic version of the atomic memory storage we achieve in the lab, but not an infinite timescale. The information of that light is not lost. It is stretched across the fabric of space-time itself, its story frozen at the edge of the black hole for all eternity. This cosmic stopping of light is a violent, extreme process compared to our gentle laboratory methods, but the underlying principle resonates. The speed of light is deeply intertwined with the local properties of space and time. In our lab, we create a local environment with cold atoms or photonic crystals that mimics, in a very small and controlled way, this kind of extreme condition. We are creating an artificial gravitational well for light, not with mass, but with precision. We are engineering a pocket of the universe where the effective rules for light's passage are different, where time, for that pulse of light, seems to stretch and slow. This connection is more than just a poetic metaphor. It is a formal analogy that physicists use to understand complex systems. The mathematics describing light in a rapidly changing medium can be similar to the mathematics describing light in curved spacetime. This means that by studying how light behaves in our lab-created artificial gravity of photonic crystals or atomic clouds, we might gain insights into how it behaves near real black holes or in the early universe. We can create tabletop analogs of cosmic phenomena, bringing the vast and unreachable scales of astrophysics into our laboratories for careful study. It is a humbling and awe-inspiring thought. The same principles that allow us to gently hold a photon in a cloud of atoms are at work at the edges of the most destructive objects in the universe. It speaks to a profound unity in physics, whether through the immense gravity of a collapsed star or the precisely applied magnetic fields of a scientist. Light can be persuaded to halt its journey. This reveals that the constant c is not just a speed, but a fundamental converter between space and time. And when we manipulate the properties of space that light travels through, whether by curving space-time with mass or by changing the refractive index with matter, we are ultimately playing with the very threads of reality. It shows us that our experiments are not separate from the cosmos. They are a tiny, focused echo of the universe's own grand, dynamic processes. We are learning the grammar of the cosmos, and in doing so, we find that our gentle, human-scale curiosities are written in the same language as the swirling galaxies and the silent, light-devouring holes in the sky. While the cosmic ballet of light bending around black holes and the serene quantum mechanical pause within an atomic cloud feel like wonders confined to the realms of theoretical physics and advanced laboratories, the principles of manipulating light's journey are already quietly at work all around us, woven into the fabric of technologies that shape our daily lives. This is perhaps the most gentle and reassuring aspect of our story, that these profound concepts are not distant abstractions, but are already whispering within the devices we rely on, making them more efficient, more powerful, and more capable. The most widespread application of slowed light is so common we scarcely give it a thought: the optical fiber. Every time you send a message, stream a video, or make a video call, pulses of light are carrying that information through thin glass threads spanning oceans and continents. But light, as we know, travels slower in glass than in a vacuum. This slowing is the very reason fiber optics work. The glass core of the fiber is engineered to have a specific, carefully calibrated refractive index, and it's surrounded by a cladding with a slightly lower index. This structure traps the light within the core through total internal reflection, guiding it along the fiber's curve. But it also means the light is propagating at roughly 2/3 of its vacuum speed. This delay is not a flaw, it is the mechanism of the technology. The information is encoded in the timing of these slowed pulses. Without this controlled slowing, this gentle persuasion of light to travel a specific path at a specific pace, our global communication network would simply not exist. We are already masters of slowing light on a global scale, even if we do not often pause to consider it. Delve a little deeper into the medical world, and you will find more exquisite examples. Optical coherence tomography, or OCT, is a revolutionary imaging technique used by ophthalmologists to create detailed cross-sectional images of the retina. It works by measuring the echo time of light. A beam of light is split in two. One half is sent into the eye, and the other is sent to a moving mirror. The light that scatters back from the different layers of the retina is then combined with the light reflected from the mirror. Because the light in the mirror arm is delayed by its journey, a delay precisely controlled by the mirror's movement, it interferes with the retinal light only if the path lengths match within the light's coherence. By measuring this interference, the system can build a micrometer resolution map of the retina. The precision of this measurement relies entirely on our understanding of light's propagation and our ability to measure its incredibly short travel time within the eye. It is a direct application of using light's journey and our control over its timing to see the unseen. In a more advanced and emerging realm, LiDAR systems, which use laser light to map environments in 3D for self-driving cars, archaeology, and geology, also depend on exquisitely precise timing of light pulses. They measure the time it takes for a laser pulse to travel to an object and back. The slowing of light by the atmosphere, though a tiny effect, must be accounted for in the most high-precision systems to ensure accuracy. Even the humble digital camera sensor in your phone is a testament to our control of light's interaction with matter. The silicon in the sensor has a property called its absorption spectrum. It absorbs different colors of light, slowing them and converting their energy into electrical signals. The design of the sensor with its micro lenses and color filter arrays is all about managing this light-matter interaction to capture a faithful image. We are guiding and slowing light to tell a story. And looking toward the very near future, the slow light technologies we've explored in the lab are poised to make the leap into these everyday applications. The optical buffers and delay lines made from photonic crystals could be integrated into the chips at the heart of data centers, managing the torrent of optical data without the inefficient conversion to electricity, reducing energy consumption and heat. Sensors based on slow light principles, where light lingers longer with the sample, could lead to handheld medical devices that detect a single virus particle, or environmental monitors that sniff out the faintest trace of a pollutant with unparalleled sensitivity. These would not be bulky lab machines, but small, integrated tools. The quantum memories that store light could become the repeaters for a secure quantum internet, their ability to hold and release quantum information intact, enabling a new era of communication. This is the quiet, practical poetry of it all. The same fundamental physics that describes a star's light slowing through our atmosphere or a photon pausing in an atomic cloud is already embedded in the technology that connects us, heals us, and helps us see our world more clearly. It is a gentle reminder that the line between profound scientific discovery and practical application is often very thin, and that our quest to understand the universe, even in its most subtle details, consistently returns to us as a gift, a new way to care for one another and to better comprehend the delicate, light-woven tapestry of our existence. As we appreciate the quiet hum of slow light technology in the world around us, it is natural to wonder if our journey of understanding is nearing its end. Have we, in our laboratories and theories, unraveled all the mysteries of light's velocity? The answer is a gentle and reassuring no. For every question we answer, the universe seems to unveil a deeper, more subtle layer of inquiry. The exploration of light's speed is not a path leading to a final destination, but a vast unfolding landscape with new horizons beckoning from the mist. Many of the most profound mysteries that remain are not about breaking light's speed limit, but about understanding the full, rich implications of its constancy and its malleability within the rules it is given. One of the greatest unsolved puzzles in all of physics lies at the intersection of our two most successful theories, quantum mechanics and general relativity. Quantum mechanics describes the universe of the very small, atoms, photons, and their strange probabilistic behaviors with breathtaking accuracy. General relativity describes the universe of the very large, gravity, planets, and the curvature of space-time, with equal power. Yet the two theories are fundamentally incompatible. They speak different mathematical languages and make contradictory claims about the nature of reality at the extremes, such as at the center of a black hole or at the moment of the Big Bang. And the speed of light, c, is the linchpin that holds both theories together, even as they disagree elsewhere. How does light truly behave in such extreme gravitational fields when its quantum nature must also be considered? Our experiments with slowing and stopping light in the lab are beautiful analogs, but they are only analogs. The true nature of space-time foam, the hypothetical turbulent structure of space-time at the Planck scale, a scale a billion times smaller than an atom, remains entirely unknown. At this scale, does the concept of a constant speed of light even hold meaning, or does the fabric of space-time itself become probabilistic and fuzzy? These are questions that current physics can barely even frame, let alone answer. Another enduring mystery revolves around the nature of light itself. We have spoken of photons as particles and as waves, but what are they fundamentally? Are they truly point-like particles, or do they have a tiny, finite size? Could there be a smaller, more fundamental constituent to light that we have not yet discovered? Some speculative theories, like string theory, propose that the fundamental building blocks of the universe are not particles, but tiny, vibrating strings. In such a framework, a photon would be a specific vibration of a string. This could potentially lead to subtle deviations from perfect constancy under certain conditions, deviations so minute we have no hope of detecting them with current technology. Furthermore, we still do not fully understand the vacuum of space. Quantum field theory tells us that what we perceive as empty space is not empty at all, but a seething, bubbling foam of virtual particles constantly popping in and out of existence. This is the quantum vacuum. Light travels through this vacuum. Does this fluctuating energy density have any effect, however infinitesimally small, on the speed of light? Could there be a tiny, inherent dispersion in the vacuum itself, meaning that light of different energies might travel at very slightly different speeds? Most experiments confirm the constancy of c to an incredible degree of precision, but the quest to find even the smallest violation is a driving force in fundamental physics, for it could be the first clue to a deeper theory. There are also practical mysteries that remain. While we have slowed light to a crawl, and even stopped it, the storage times in quantum memories are still short, on the order of minutes at best. How can we extend this to hours or days? What are the ultimate physical limits of quantum memory? And can we create wide bandwidth slow light capable of slowing complex, information-rich pulses without distortion? a necessity for real-world optical computing. Finally, there is the mystery of consciousness itself. We have spoken of light as a carrier of information. Our eyes detect it, and our brains interpret it to construct our reality. But the hard problem of consciousness, how and why we have subjective experience, remains untouched by physics. We can describe the path of a photon from a star to a retinal cell to a neural impulse with perfect accuracy, but we cannot explain how that cascade of electrical signals transforms into the subjective experience of seeing a twinkle, feeling wonder, or listening to a story about light itself. The journey of the photon is a physical one. The journey of perception is a mystery. These unanswered questions are not a failure of science, but its lifeblood. They are the open invitations, the gentle whispers that call to the curious, the next generation of scientists who will design experiments we cannot yet imagine, who will peer into the quantum foam and the depths of black holes with new tools and new ideas. The story of light is far from over. It is an eternal story, and we have only just begun to read its opening chapters. The mysteries that remain are a promise that the universe will always have more wonder to offer, more beauty to reveal to those who are willing to look slowly, carefully, and with an open and peaceful heart. In the quiet contemplation of light's mysteries, both solved and enduring, we find ourselves reflecting on the impulse that drives this entire endeavor. It is an impulse that transcends mere technical achievement or practical application. The centuries-long quest to understand light, to measure its speed, to gently persuade it to slow its eternal rush, is perhaps one of the purest expressions of the human spirit's desire to connect with the universe. It is a story not just of photons and atoms, but of curiosity, patience, and a deep, abiding wonder that has illuminated our species since we first looked up at the stars. Consider the long arc of this journey. For most of human history, light was a profound mystery, a divine gift, something to be revered but not understood. Ancient philosophers pondered its nature. Then came the first scientific thinkers like Ibn al-Haytham in the Islamic Golden Age, who began to experiment with reflection and refraction, laying the groundwork for optics. Later, Galileo tried to measure light speed with lanterns on distant hills, a humble beginning to a quest for precision. Each step required a leap of imagination and a dedication to observation. The 19th century brought us Maxwell's beautiful equations, unifying electricity and magnetism and revealing light as an electromagnetic wave. This was not just a calculation. It was a moment of profound cosmic connection, a realization that the same principles governing magnets and electric currents also governed the light from the stars. Then came Einstein, who, by taking the constancy of the speed of light as a postulate, unraveled the nature of space and time themselves. This was a testament to the power of human thought, that by trusting in the fundamental harmony of the universe, we could rewrite our understanding of reality. And now, in our era, we have reached a point where we can not only measure this fundamental constant with astonishing precision, but can also interact with it intimately, asking light to pause and converse with matter. This entire history is a slow, collective meditation. It is built on the work of countless individuals, each contributing a small piece of understanding, often without knowing where the path would lead. It is a project of shared curiosity, a conversation across generations. The scientist in a modern lab, cooling atoms to a billionth of a degree above absolute zero, is standing on the shoulders of all those who came before, from the philosophers of antiquity to the theorists of the last century. This shared quest reflects a deep human need to not just exist in the universe, but to understand our place within it. By learning the rules that govern something as fundamental as light, we are, in a way, learning the grammar of the cosmos. We are learning to read the story of existence. This pursuit is also an act of humility. Every time we devise an experiment to test the speed of light, we are essentially asking the universe a question. And we must be prepared to accept the answer, even if it challenges our most deeply held assumptions. This respectful dialogue with nature, this process of asking, listening, and adapting our understanding is a form of reverence. It is a recognition that we are part of a reality far greater and more mysterious than ourselves, and that our role is not to conquer it, but to learn from it with patience and awe. Furthermore, the methods we use speak to a certain philosophy. We do not bully light into slowing down. We do not command it. We create conditions of such exquisite tranquility and order, ultra-cold temperatures, perfectly structured materials, that light willingly, almost naturally, changes its behavior. We invite it to slow down. This approach of gentle persuasion, of creating resonance and understanding, is a powerful metaphor for how we might interact with the world and with each other, not through force, but through empathy, through the creation of conditions where beauty and cooperation can emerge. Finally, this entire journey is a source of quiet comfort. In a world often dominated by noise and haste, the study of light reminds us of the value of slowness, of precision, of taking the time to truly see. It reminds us that some of the most profound truths reveal themselves not to the rushed and the frantic, but to the patient and the observant. The twinkle of a star is a message that has traveled for millennia. The slow pulse of light in a lab is a story being told over milliseconds. Both operate on timescales far removed from our daily rush, and both invite us to expand our sense of time, to slow down our own minds, and to appreciate the deep, slow rhythms of the universe. So, as we near the end of our exploration, know that this story is ultimately a human one. It is about our endless, peaceful curiosity, our desire to reach out and touch the cosmos, and the profound connection we feel when we realize that the universe is not a cold, mechanical place, but a realm of elegant, understandable beauty, waiting for us to learn its language, one photon at a time. Our journey with light has thus far followed a single luminous thread, the visible light that paints our world in color and carries starlight across the cosmos. But this thread is part of a far grander tapestry, a vast and continuous spectrum of energy that stretches far beyond the narrow window our eyes can perceive. This is the electromagnetic spectrum, and the speed of light, that constant c, is the unifying rhythm that binds all of its varied expressions together, from the longest, languid radio waves to the most furious, penetrating gamma rays. This realization is a profound source of wonder. The same fundamental phenomenon, an oscillating, self-propagating electromagnetic field, manifests in forms that seem utterly different to our senses, yet all march to the same timeless drumbeat, all travel at the same ultimate speed through the vacuum of space. Consider the humble radio wave. Its wavelength can be as long as a mountain, its oscillations so slow and gentle that they seem to belong to a different universe than the frantic, tiny wavelengths of visible light. Yet, when you tune your radio to a station, you are harnessing these gentle giants. The information encoded in them, a voice, a song, has traveled from a broadcast tower, moving at the speed of light, to be decoded by your receiver. These waves wash over us and through us constantly, an invisible ocean of slow, rhythmic energy, each wave a testament to the constancy of C. Move higher in frequency and we find microwaves. Their shorter, more energetic wavelengths are perfectly tuned to interact with water molecules, which is why they can so efficiently heat our food. But they are also the faint afterglow of the Big Bang, the cosmic microwave background radiation that permeates all of space, a cooled remnant of the universe's fiery birth that has been traveling at the speed of light for over 13 billion years to tell us the story of creation itself. Then comes infrared light, which we feel as heat. Every object warmer than absolute zero radiates this energy. The warmth you feel from the sun or from a loved one's hand is infrared radiation, emitted and absorbed, traveling at light speed, carrying the thermal signature of the world. It is an invisible light of connection and comfort. And then, at last, we arrive in the narrow sliver of the spectrum we call home, visible light. This is the tiny range of frequencies that our eyes evolved to detect, a specific harmony in the vast electromagnetic symphony that corresponds to the energies most abundant in the light from our sun. The different colors, red, orange, yellow, green, blue, indigo, violet, are simply notes in this harmony, each with a slightly different frequency and wavelength, yet all traveling, always at the same speed. Beyond violet lies ultraviolet light, invisible to us but powerful enough to tan or burn our skin. It is a light of both danger and necessity, and it too races toward us from the sun at 300 million meters per second. Further still are X-rays, with their ability to pass through soft tissue but be absorbed by bone, allowing us to see the hidden architecture within. And finally, the gamma rays, the most energetic photons of all, born in the most violent events in the universe, supernovae, neutron star collisions, and the voracious accretion disks of black holes. Their frequencies are astronomically high, their wavelengths subatomic. They carry immense power, the power to destroy or to create. And they too, like a leisurely radio wave, travel at the speed of light. This is the breathtaking unity of it all. The same fundamental force, governed by the same equations, expresses itself across an unimaginable range of scales, yet never once violates the cosmic speed limit. Whether it is a radio wave carrying a symphony across a continent, or a gamma ray carrying the news of a star's death across galaxies, the messenger is the same, and its speed is unwavering. This constancy is what allows the universe to be coherent, to be understandable. It means that the laws of physics are the same everywhere. When we look at a distant galaxy in radio waves, visible light, and X-rays simultaneously, we are seeing different aspects of the same event, all delayed by the same travel time, all telling a unified story. The speed of light is the great synchronizer of the cosmos, and when we slow light down in a laboratory, we are not just slowing down visible light, we are manipulating this fundamental electromagnetic wave. The principles of electromagnetically induced transparency, or photonic crystals, can, in theory, be applied to other parts of the spectrum. We could, perhaps, one day slow down a microwave or a radio wave, creating buffers for different types of information, or designing new kinds of sensors. The constant C is the rule, and our manipulations are the gentle, local exceptions we carve out within that rule, tiny eddies in the great, constant flow of electromagnetic energy that is the universe. This symphony of waves, from the lowest bass note to the highest piercing shriek, all moving to the same rhythm, is a source of deep peace. It speaks of a universe that is not chaotic, but ordered, not arbitrary, but lawful. It is a harmony written into the fabric of reality itself, a harmony we are only just beginning to hear and understand in all its magnificent light-speed complexity. As we immerse ourselves in the vast symphony of the electromagnetic spectrum, a deeper, more fundamental harmony begins to emerge, one that transcends mere propagation and touches upon the very nature of existence itself. This is the dance between light and matter, a relationship so intimate that it reveals them not as separate entities, but as different manifestations of the same underlying energy, two sides of a single cosmic coin. This concept, perhaps one of the most beautiful and profound in all of physics, finds its purest expression in Einstein's iconic equation, E equals mc squared. This deceptively simple formula is a declaration of equivalence. It tells us that energy and mass are interchangeable, and that the exchange rate is governed by the square of the speed of light. The c squared here is not just a number, it is a constant of cosmic proportions, a multiplier so vast that it reveals the immense energy locked within even the tiniest amount of matter. But this equation is not merely a theoretical statement, it is a recipe for transformation, and light is often the currency of this exchange. Consider the process of pair production, a phenomenon where light, in its purest form, as a high-energy gamma-ray photon, transforms directly into matter. In the emptiness of space, if a gamma-ray photon possesses enough energy, an energy equivalent to the mass of 2 electrons, it can spontaneously transform into an electron and its antimatter counterpart, a positron. Here, light ceases to be light. Its energy, its very essence, condenses into particles with mass. Particles that will now move at speeds less than the speed of light, particles that have weight and substance. The photon, the massless traveler, has given birth to matter. The reverse process is just as elegant. When an electron and a positron meet, they annihilate each other. Their mass is not destroyed, it is converted. In a flash of energy, they become 2 gamma-ray photons, their material existence dissolving back into pure light, which then speeds away at the speed of light. This is the cycle: light to matter, and matter back to light. It is a dance of creation and annihilation, with the speed of light serving as the constant, the conversion factor, the unwavering rule that governs the transaction. This interchangeability is not limited to such extreme particle interactions. It is the principle that powers the stars. Deep in the core of our sun, under immense pressure and temperature, protons, the nuclei of hydrogen atoms, collide and fuse together. In this process, a tiny fraction of their mass is lost. That mass does not vanish, it is converted into energy, primarily in the form of light, photons of gamma radiation. These photons begin a long, slow journey outward from the core, constantly being absorbed and re-emitted, their energy slowly degrading through the layers of the star until finally, after thousands of years, they emerge from the surface as the visible sunlight that warms our planet and gives life to our world. The warmth on your skin is literally mass transformed into light. Every leaf that grows through photosynthesis is building itself with sunlight, with energy that was once the mass of hydrogen in the sun. We are, in a very real sense, made of starlight, and the speed of light is the constant that allowed that transformation to happen. This deep connection between light and matter also helps us understand why slowing light is even possible. When light enters a material and slows down, it is because it is interacting with the electrons within that material. But what are electrons? They are matter with mass. And what is light? It is energy without mass. In their interaction, they are not separate. They are engaging in a tiny, continuous dance of energy exchange. The light's energy is temporarily stored in the motion and configuration of the electrons. It is, for a fleeting instant, expressed as a form of potential energy within matter, before being released again as light. The light pulse's slowdown is a manifestation of this temporary storage, this brief hesitation where energy flirts with becoming matter before continuing on its way. This reveals that the act of slowing light is not a violation of its nature. but an embrace of its deepest relationship with the substance of the universe. We are not breaking light. We are inviting it to dance more closely with matter, to linger in that state of intimate exchange, to reveal the beautiful hidden connections that bind the ethereal to the tangible, energy to mass, the photon to the atom. It is a reminder that the universe is not a collection of separate things, but a flowing, transforming whole, and that the constant speed of light is not just a speed limit, but the fundamental rhythm of that transformation, the beat to which all existence dances. So, we return to our central, gentle question. Can we, in any meaningful sense, truly slow down the speed of light? The answer, as we have seen, is a nuanced and beautiful yes, but it requires us to understand what we mean by slow down. We are not breaking a universal constant, we are engaging in a profound manipulation of light's journey through its interaction with matter. The speed of light in a vacuum, c, remains the universe's unwavering constant, the ultimate speed limit for information and causality. This fundamental speed is a property of space-time itself. What we are slowing is light's propagation through a medium, its group velocity, the speed at which a pulse of light and its information travel. This is not a mere technicality, it is the heart of the phenomenon. And the methods for achieving this are as diverse as they are ingenious, each a testament to our growing ability to converse with light. We began with the simplest form, the passive slowing that occurs in any transparent material, like glass or water. Here, the light's electric field polarizes the atoms in the material, inducing tiny dipoles that oscillate and re-radiate the light. The resulting interference between the original wave and these newly generated waves creates a net wave that propagates more slowly. The light is continuously being absorbed and re-emitted in a coordinated way, and this process introduces a delay. The light within the medium is genuinely traveling slower than it would in a vacuum. This is a bulk effect, a statistical average across trillions of atoms. But we can go much, much further than this. By moving beyond passive materials to actively controlled systems, we can persuade light to slow to a crawl. The use of ultra-cold atomic clouds, like Bose-Einstein condensates, allows for a much more intimate and dramatic interaction. Here, we use the principle of quantum interference, precisely manipulating atomic energy states with control lasers to create a condition called electromagnetically induced transparency. This effect makes an otherwise opaque cloud transparent to a very specific frequency of light, but it does so by creating an extremely steep dispersion relation. In this steep region, the group velocity of a light pulse plunging into this cloud can be reduced to mere meters per second, even centimeters per second. The light is not being absorbed and re-emitted in a stop-start fashion. Rather, its energy is coherently coupled to the collective quantum state of the entire atom cloud, creating a hybrid quasi-particle called a polariton. This polariton, being part matter, has effective mass and inertia, and thus moves slowly. We are essentially dressing the light in a cloak of matter, persuading it to adopt the slower, more deliberate pace of the atomic world. And we can go further still, to a complete stop. By adiabatically turning off the control laser while the light pulses inside the atomic cloud, this coupling can be manipulated such that the light's quantum information, its phase, amplitude, and polarization, is perfectly mapped onto a collective spin state of the atoms. The light, as light, ceases to exist. Its information is stored in the patterns of atomic spins. The velocity is not just slow, it is zero. The light has been stopped, its story written into atomic memory. Later, turning the control laser back on reverses the process, reading the atomic memory and re-emitting a perfect replica of the original light pulse, which then resumes its journey at speed c. Beyond these atomic methods, we have structural methods. Photonic crystals, materials with a periodic nanostructure that affects the propagation of light, can also dramatically reduce light's group velocity. By designing a crystal with a photonic band gap, light of certain frequencies is forbidden from propagating. At the edges of these band gaps, the dispersion relation again becomes very steep, and light's group velocity drops precipitously. Here, the slowing is achieved through countless tiny scatterings and interferences within the crystal's lattice. The light is forced to take a vastly more convoluted path, drastically reducing its forward progress. Metamaterials, with their artificially engineered sub-wavelength structures, offer another path. By designing unit cells that resonate strongly with specific light frequencies, they can create regions of exceptionally high effective refractive index, which correspondingly slows the light passing through them. So, the answer is a resounding yes. We can slow light down. We can slow it dramatically from its vacuum velocity of 300 million meters per second to the pace of a bicycle, a walking human, or even to a complete and utter standstill. We achieve this not by force, but by invitation, by creating exquisitely tailored conditions in which light willingly engages with matter in a way that retards its own progress. We are not breaking the laws of physics, we are exploring their beautiful and subtle depths, learning how to gently guide the universe's fastest traveler to pause and rest for a while. Having established that we can indeed slow light to a profound degree, even bringing it to a full stop, it is natural to wonder about the practicalities of such an endeavor. These are not simple parlor tricks. They represent the pinnacle of experimental control, and each method exists within a delicate balance of immense challenges and exquisite precision. The path to slowing light is strewn with obstacles that must be patiently, gently overcome. And understanding these limitations reveals just how extraordinary the achievement truly is. Perhaps the most significant challenge is loss. As we coax light to move more slowly through a medium, we are also increasing its interaction with that medium. A slower light pulse is a more compressed light pulse, its energy concentrated into a smaller volume. This intensified interaction heightens the risk of absorption and scattering, processes that steal the light's energy, converting it into heat or random, useless photons, effectively destroying the very pulse we are trying to preserve. It is like trying to guide a delicate whisper through a crowded, noisy room. The longer it takes, the more likely it is to be drowned out. In atomic systems, this means the atoms must be prepared in states that are exceptionally stable and well shielded from external magnetic fields and collisions. Any disturbance can cause decoherence, breaking the fragile quantum state that allows for the slow light propagation. In photonic crystals and metamaterials, the structures must be fabricated with near-perfect precision. Any microscopic defect or irregularity in the nanostructure acts as a scattering center, sapping the light's strength. The quest to slow light is therefore also a quest for perfection, for ever purer materials, ever colder temperatures, and ever more stable environments. Another fundamental constraint is bandwidth. The extreme optical effects used to slow light, such as electromagnetically induced transparency or the band edge effects in photonic crystals, are typically very narrow band phenomena. They work for a very specific color, a very precise frequency of light. A perfect monochromatic laser beam can be slowed dramatically. But a pulse of light carrying complex information is not a single frequency. It is a packet of many frequencies. If the slow light medium does not slow all these frequencies equally, the pulse will become distorted as it travels. Its shape will change. It will spread out or become compressed in time, corrupting the information it carries. Creating a slow light system with a wide bandwidth, one that can handle a complex, information-rich pulse, is an enormous challenge that remains at the forefront of research. There is also the challenge of the delay bandwidth product. This is a key figure of merit that represents a trade-off: how long you can delay a pulse versus how much information, bandwidth, that pulse can contain. You can have a very long delay for a very simple narrowband pulse, or a very short delay for a complex wideband pulse. But achieving a long delay for a wideband pulse is exceedingly difficult. It is like trying to park a long train in a short station. The constraints are inherent to the system itself. For applications like optical buffering, where you might want to store large amounts of data as light, this is a critical limitation. Furthermore, there are the sheer practical difficulties of the systems themselves. The atomic vapor cells and Bose-Einstein condensates that produce the most dramatic slowing effects require massive, complex apparatuses. They involve ultra-high vacuum chambers, powerful lasers for cooling and trapping, and sophisticated magnetic fields. They must be isolated from vibrations and external noise. These are not devices that can be easily miniaturized or integrated into a practical photonic chip, at least not yet. The pursuit is toward integration, toward creating slow light effects in solid-state systems, like specially doped crystals or on-chip photonic structures that can operate at room temperature. But this often comes at the cost of the extreme slowing factors possible in cold atoms. Finally, there is the challenge of retrieval. When light is brought to a complete stop, its information is stored in the quantum state of the atoms. But quantum states are fragile. They are subject to decoherence, the loss of quantum information, through interactions with the environment. The storage time is limited by how long this coherence can be maintained. Researchers constantly work to extend these coherence times through better isolation, pure materials, and clever quantum error correction techniques. But there is always a finite limit. The light can be stopped, but it cannot be held forever. These challenges are not discouragements. They are the boundaries that define the field, the puzzles that invite deeper understanding and more creative solutions. Each obstacle overcome is a step toward harnessing the full potential of slow light, toward a future where we can truly manage the flow of light with the same ease with which we now manage the flow of electrons. As we acknowledge the delicate challenges inherent in persuading light to slow its eternal pace, we can now turn our gaze forward to the gentle horizons of possibility that current research is beginning to illuminate. The field of slow light is not static. It is a river of inquiry, constantly flowing and branching into new and unexpected territories. The future directions of this research are focused on overcoming the present limitations, not through force, but through ever deeper understanding and increasingly elegant designs, aiming to transform these laboratory marvels into foundational technologies for a new era. A primary and deeply compelling goal is the pursuit of integration and miniaturization. The breathtaking experiments with ultra-cold atoms, for all their beauty, are conducted within apparatuses that fill entire rooms. The future lies in translating these quantum phenomena into solid-state systems that can operate on a microchip at room temperature. Researchers are exploring a multitude of paths to achieve this. One promising avenue is the use of rare earth ion-doped crystals. These materials have atoms whose electrons can be manipulated into long-lived quantum states, similar to the atoms in a vapor, but they are locked in a solid, stable matrix. By using lasers to prepare these doped crystals, scientists can create slow light effects and quantum memories that do not require immense cooling systems, making them far more practical for real-world applications. Another path is the continued refinement of photonic integrated circuits. Here, tiny waveguides made from materials with high nonlinearities or intricately patterned as photonic crystals are etched onto semiconductor chips. The dream is to create an all-optical processor where light, not electricity, carries and processes information, and where slow light elements act as buffers and delay lines, managing the flow of data with minimal energy loss and heat generation. This would represent a quiet revolution in computing, moving us from the era of electrons to the era of photons. Alongside this push for practicality, there is a drive toward enhancing performance, extending storage times, increasing bandwidth, and reducing losses. This involves delving into more complex quantum control techniques. The use of dynamical decoupling, for instance, where a series of precise laser pulses are applied to a quantum memory, can effectively echo away the disruptive influence of the environment, protecting the stored light information for much longer periods. Another frontier is the exploration of new material systems altogether, such as topological photonics. In this emerging field, researchers design materials where light waves are protected from scattering by topological properties, much like a traveler on a protected pathway who cannot be easily pushed off course. This inherent robustness could lead to slow light waveguides that are immune to the defects and imperfections that currently cause so much signal loss, potentially enabling unprecedented control over light's flow with near-perfect efficiency. Furthermore, the concept of slow light is expanding beyond a single pulse in a single medium. Researchers are beginning to explore the dynamics of stopped light interfaces, where two separate quantum memories, each holding a stored light pulse, can be made to interact with one another through their atomic states. This would allow for the performing of logical operations on the quantum information carried by the light, without it ever being converted into electricity. It is a step toward a truly quantum network, where information processing happens through the direct interaction of stored photons, a world of all optical quantum computation. And finally, the most profound future direction may be the use of these controlled slow light systems as simulators for other intractable problems in physics. The way light behaves in these complex, engineered materials can be mathematically analogous to how electrons behave in exotic superconductors or how space-time behaves near a black hole. By carefully tuning a slow light experiment, a physicist can, in effect, create a tabletop universe with custom-made physical laws, using light as a probe to understand mysteries that are otherwise beyond our reach in the cosmos. This is the gentle, patient future of slow light, a convergence of material science, quantum engineering, and fundamental physics, all aimed at gaining a deeper mastery over the flow of light. It is a future not of overwhelming light, but of understanding it so intimately that we can invite it to dance to a slower rhythm, to rest in our hands for a time, and to help us build a world that is more connected, more efficient, and filled with a deeper, more profound wonder. And so, we arrive at the gentle close of our exploration, a return to the quiet room from which we began, with the starlight still patiently arriving at the window. Our journey has taken us from the vast, empty stretches of space where light travels at its ultimate, constant speed, to the crowded realms of matter, where it is persuaded to slow its pace. We have seen how a pane of glass, a prism of water, or the very air we breathe can gently retard light's progress in a passive, everyday miracle. We ventured further into the profound cold of laboratories where atoms are lulled into near-perfect stillness, and light is not just slowed, but invited to pause completely, its essence transferred into the silent spin of atoms held in a quantum embrace before being released once more, unchanged, to continue its journey. We considered the intricate architectures of photonic crystals and metamaterials, human-made structures that guide light on longer, more meandering paths, convincing it to linger through design rather than temperature. We acknowledge the challenges, the delicate balance against loss, the narrow bandwidths, the fragility of coherence, all the gentle obstacles that make this feat so remarkable, and we look to a future where this understanding is refined, integrated, and woven into the fabric of new technologies, from quantum networks to analog computers, all born from the ability to gently hold the universe's fastest thing. Through it all, the fundamental truth remains. The speed of light in a vacuum, c, is unwavering. It is a constant upon which the cosmos is built, the thread that stitches space and time together into a single fabric. Our achievements in slowing light are not violations of this law, but beautiful and subtle conversations within its rules. We have learned to create local conditions, tiny pockets of the universe, where the dialogue between light and matter is so intimate that light willingly adopts a slower rhythm. We have not broken the constant, we have learned to compose new melodies using its unwavering beat. This journey, in the end, is a testament to human curiosity and patience. It is a story of looking at a starry night, not just with wonder, but with a deep, questioning peace. It is about wanting to understand the light, to know its nature so intimately that we can whisper to it and ask it just for a moment to rest. This pursuit mirrors a deeper yearning within us, to find moments of slowness and stillness in our own lives, to create pockets of peace within the relentless rush of time. The light from those distant stars has traveled for millennia to reach you. It has passed through clouds of dust and gas, through the atmospheres of planets, and finally through your window. Its journey is a story of constancy. But here, on Earth, we have learned to add a new, gentle chapter to that story, a chapter where light can be asked to pause, to be held, and to be studied before it continues on its way. This ability is a profound gift. It tells us that the universe is not a rigid, impersonal clock, but a place of infinite subtlety and grace, a place that responds to careful, respectful inquiry. It tells us that even the most constant things have hidden depths, and that by approaching them with patience and wonder, we can uncover beauties we never imagined. So as you drift towards sleep, let the thought of this gentle persuasion bring a sense of peace. The universe is knowable, yet endlessly mysterious. It operates by steadfast rules, yet within them allows for breathtaking creativity and gentle manipulation. The light slows, and in its slowing, it reveals not a weakness, but a depth, a capacity for connection and dialogue between the energy of the cosmos and the matter that makes up our world and us. We are part of this dialogue, both observers and participants in a universe that is forever whispering its secrets to those who are willing to listen, slowly, and with an open heart. Rest now, surrounded by light that has traveled an eternity to be here, and know that its journey, and ours, is filled with a calm, constant, and beautiful wonder. Good night, observer of the light. We will meet again in our next journey.